I am Diego, co-founder of Aligned and head of research. And I am going to be talking a little bit about zkVM design choices and how to build the apps with Aligned. So the idea is that we are interested in building these decentralized applications, and basically blockchains are verifiable computers, and they achieve this property by two things. We have each node re-execute everything and then reach consensus. The problem with this is that this is not efficient because all the nodes have to do the same work, okay? And so this affects scalability. With zk proofs, what we can do is basically have just one party generate a proof of the correctness of the computation and then verify it much faster than using naive re-execution. Okay, and this allows us to add like more computers to the blockchain and make it faster because each can execute on their own and then the rest just has to verify zk proofs. Okay, but let's jump a little bit to these proofs, and the idea is that we can use them to prove different programs, and we can generate a proof system if we can build it for an NP-complete problem, for example, R1CS or Boolean circuit satisfiability. And then what we can do is kind of compile any program we want to prove, any NP program to this NP-complete, and then prove it. Of course, there are like different proof systems, and they have like different trade-offs regarding, for example, proof size, verification time, prover time, whether they are not post-quantum secure, and then how easy it is to do recursion. Okay, so you have like different techniques to choose from. So the problem with this is that, as I was telling you, you have to compile your program to some language that you can use to prove your computation. So it's the normal thing was building something called arithmetic circuits, and so what you need is something to compile your code to that. I remember Neil was doing precisely a zkLLVM, and that was like super interesting because then you write your code in a high-level language, and then it gets compiled to circuits. Some people have been developing zk DSLs. For example, that's the case of Noir by Aztec. And then another alternative was, okay, instead of having to code a circuit for every program that we want to run, we generate the circuit for a virtual machine, and then what we do is prove the execution of a particular program on top of the zkVM. Okay? And that, in principle, should be easier because developers don't have to code these circuits by themselves. They just write their high-level language code, and then it gets compiled and proven by the VM. So there are like different choices for zkVMs. They have to do, for example, with instruction set architecture, different like proof systems. Another important design choice is whether it is monolithic or modular, the underlying field. I will try to explain some of these things. The first one is, of course, the instruction set architecture. You have like ordinary or widely known VMs, for example, instruction set architectures such as, for example, RISC-V. Okay, you have a very clear specification. They are rather simple. A lot of people understand it, and so you're using something people already know, and you could, for example, have Rust code compiled to RISC-V and then execute it on top of the VM, and that offers you several advantages. Of course, a drawback is that RISC-V was not developed with zk in mind, So representing these ISA as arithmetic circuits can be quite challenging, and it may not be the most efficient thing to prove. Of course, other people chose to build their own custom. The first one was the Cairo VM, which relies on the Cairo ISA, okay? But the problem is then people have to learn a new language, which is Cairo. But the good thing is you can represent it more efficiently. And some people took another go, which is, okay, I am going to have my own custom thing, but then what I am going to do is take like RISC-V and then try to connect it with this new thing I created. I think that is the case of a VM called Lita, and then you have to build like a custom compiler to be able to do that. Of course, then there is a big struggle regarding proof system, and this affects a lot proof sizes and verification times, prover efficiency, and everything. There are basically two groups. You have, for example, elliptic curve based. That was the road, for example, taken by Nexus zkVM originally. The reason is it may be easier to build proof systems that are actually zero knowledge and don't leak important information that is important if you want to do or to have privacy. And then you had all the hash-based proof systems. The advantage of hash-based proof systems is that first, they are post-quantum secure. They don't rely on the discrete log problem, which is the case of elliptic curve cryptography. And you have like more flexibility to choose your finite field, because what you do basically is to prove something, you represent everything as a set of equations over some finite field. And the problem with elliptic curves is your field is fixed. It's given by your elliptic curve. And so if you want to represent, for example, a simple Boolean variable, you still have to represent it by a single field element, which can be like 256 bits long. So you have a huge overhead to represent variables. In the case of hash-based proof systems, you can choose smaller fields. For example, you could use Mersenne primes, which take only 31 bits. And so by doing that, you reduce a lot the overhead. Of course, there is a new trend, which is binary fields that are even more efficient, because with them, you can represent any variable without overhead. Okay, you have to pay a little bit more on the complexity of the fields, but it's more efficient. Then we have also a very important design choice, which is whether your VM is going to be just one CPU and nothing else, or whether you are going to have your CPU and several other components to which you are going to delegate computation. The first VM, the Cairo VM, was monolithic. You just had the table for the VM. And the problem with that is if you want to do some computations, it may not be super efficient. So what they did then was, okay, let's add like some specialized operations for elliptic curves, for example. But the problem was that you had to create a table layout that was not useful for all the problems you wanted. Maybe that layout was a bit big for the program you wanted to prove, and then you had a lot of overhead. On the other hand, modular VMs, what they do is then they have separate coprocessors, and then what you can do is basically expensive operations, delegate them to one of these specialized units. The drawback is that Proof sizes tend to be a lot larger because you have to generate a separate proof for each component. But in general, most VMs right now go for this approach because it offers a lot more flexibility. Regarding finite fields, there are like lots of popular choices. Then in general, all VMs right now rely on lookup arguments. They have different techniques, but right now it seems that lookup has taken advantage. Then another thing that is a bit complex is related to memory argument. Right now, many are going for elliptic curve based memory argument, but the problem there is that you are sacrificing post-quantum security. So if you're using Starks, which is what many people use, then you are like losing that. And then you have to think about things such as proof recursion. That is to say, I can create a proof that I verified two proofs, and so I can compress. That is the approach taken by many modular VMs because they generate big proofs, and then if you want to post that on chain, it's super expensive. So what they do is then use this recursion to shrink the proofs. Of course, this makes proving slower. Some people even go further, and what they do is, in order to reduce costs of verifying it in Ethereum, they wrap it. They again do proof recursion to wrap it into a GROT16 proof, which is kind of the smallest and cheapest you can have on Ethereum. And of course, you have the issue of whether you want it or not to be post-quantum secure. Here are like some popular VMs. Cairo was the first one. Then you have Maiden. It has its own custom ISA. It introduced a separate table to deal with specialized units called chiplets. Then you had RISC-0, which was the first one to implement the RISC-V instruction set architecture. Lita took the approach of having a dedicated compiler, but using a custom instruction set architecture. SP1, Jolt has a different approach. It uses a lot of lookup arguments to check everything, and it's based on multilinear polynomials. Nexus, I think they are doing like some changes. Originally, they wanted to go with elliptic curves because you have folding, and that way you can keep memory footprint very low. You have CISC by Polygon, recently Pico. And what we are seeing is basically that a lot of teams are trying to build their own VM, but this is going to get sooner or later a bit commoditized. So here is just for you to see the process, but in general what you do is you execute the code on the VM generates the trace and the memory, and then there is a proof system that is going to process that and generate the proof. Here is the case for Starks. Then once you have the proof, you have to verify it on chain, and verification is pretty straightforward. You check that the proof is well formed, the public inputs are correct, you get the necessary verification parameters, so you run the algorithm. If it's true, it's all okay. And this is fast in any device, but on chain it has like some challenges. In Ethereum, the problem is, first, you have bounded computational power. You cannot exceed the gas limit. You cannot parallelize, so you cannot make it like faster. You don't have like any hardware acceleration. You have to optimize always the code for gas consumption because that's your relevant metric. You want to reduce costs. But the problem is that the cost also depends on the availability of precompiled contracts. And so this limits you the kind of proof systems and techniques you can use to verify things on chain. And here is an idea, but even a GROT16 proof is more or less $6 or more. So it's complicated, and even some proofs are like impossible to verify. They would be super expensive. So we have like two things that affect zk adoption. On the one hand, the proof generation. I think that the VMs and everything are solving that, or having the case of the zk LLVM. But the problem is still verification is expensive, and to reduce proof costs, either you have two strategies. You batch lots of proofs together using proof recursion, and you verify that single proof on chain, and then it's amortized, or you build your own blockchain and get rid of all the problems related to the EVM. So this is an idea of proof recursion, but basically you get two proofs and then you combine them and you get a single one. But building your own blockchain is kind of inconvenient because you have to bootstrap its security, design it, everything. So this is where it gets interesting, because with EigenLayer, what you can do is basically bootstrap the security of your layer or your network thanks to restaking, and so you can build a lot of applications on top of Ethereum without competing for block space. So what we did is then, okay, we are going to build a decentralized network to verify these proofs, but we are not going to build a separate blockchain. And of course, we are going to also provide a way of having people do proof recursion and post that on chain. And that is the idea of behind Aligned. And so there you can get, like, for example, faster bridging. You can get verifiable machine learning. zk oracles make on-chain gaming easier and less costly. And well, the idea is that then with these low verification costs for proving and verifying, this technology will get massive, because the cost of adding zk will be negligible, and the guarantees that it offers you are way more convenient. And here is the idea behind Aligned. Basically, what you have is users send their proofs and information to a batcher. The batcher just generates with all that information a single Merkle tree. It posts the root to the service manager, and that will create a new task. And we store all the data in some data service. Then when the operators see that there is a new task, what they do is they download everything, and each of them is going to run the verification algorithm for each of the proofs. And if all the proofs are correct, what they are going to do is then sign a message using a BLS signature with the root saying, okay, this is correct. And then this gets sent to a signature aggregator. And if there is quorum, then that signature gets sent to Ethereum. And once that is verified on Ethereum and it's valid, the state of that batch is changed to valid or verified. And so then the batcher responds to the user with the verification data, which is basically a Merkle authentication path to show that their proof is included in that batch. Okay, and it's pretty easy. You get parallelization because these things are running in ordinary computers, so it's pretty cool. We even got on testnet more than 4,000 proofs per second, so it's really nice. And well, one example that we used was, for example, to build the Mina bridge, but that's not important right now. But we can talk later because we are mostly on time. And then, well, the idea is that we have the AVS to build different services, and we can combine them to build a verification layer, and with that we can solve these scalability issues. Then, of course, we have the other hand related to the zkVMs. We saw that there are different trade-offs, mostly related to proof systems and whether you want a modular VM, a monolithic VM, and some other design choices. But well, happy to continue talking with you later. So thanks a lot.
Could you just run down once more the broadband slide? It's something with bandwidth. Yeah.
Yeah. Yeah, the idea is that we are going to make zk so cheap that it's going to be used like everywhere. And this is, we thought of the example of the internet before having the broadband. It was kind of very limited. It was not widely used. And then with broadband, you had lots of different applications on top of the internet. You had the birth of YouTube, social media. And so we hope that by solving developer issues related to, okay, I have to write a zk application, but you have VMs, and at the same time, the cost of using this technology is negligible. The combination of two may make zk go mainstream.
So I'd assume there are a multitude of factors, but I guess top three that comes to my head is DevX, like the easiness of kind of writing zk circuits. And then the second one would be the point you made about Eigenlayer, using cryptoeconomic security to actually bootstrap these infrastructure. And thirdly, your point around how zk proof system would actually be commoditized in the future. So I'm curious, um, how how significant is the whole Eigenlayer or the cryptoeconomic security? And with the caveat that, I mean, Eigenlayer is not perfect, obviously. And second of all, although a lot of the zk proofing system would become commoditized, it wouldn't 100% like be unilateral quality or like of zk proof between different, like you mentioned, process, for example. So I'm just curious how that kind of connects back to the broadband point.
Okay, so yeah, the good thing with Eigen is precisely uh, that you can bootstrap the network and then get very high throughput, because the problem with Ethereum is you can verify at most like 10 proofs per second. And if you want this to be used like on a massive scale, then you need to have like higher throughput. And in that sense, of course, you could build like your own blockchain, but the problem is then you are like moving outside of Ethereum. So I think this was like a good solution. Of course, Ethereum has its own roadmap with the Beam chain and everything that uh, can for sure increase a lot the throughput and then make it like simpler. On the other hand, related to proof systems, I think this is something that happens naturally with technology. At first, it's hard to understand. There are like few people that really can build. But if we are successful, a lot of the complexity and everything will be under the hood. People will just care, okay, to write on their like high level language, and then there will be like some black box that does some magic. Of course, you could say you have like different projects building different VMs, but really in the end, it's just choosing which of those VMs. I don't think there will be a competitive advantage. Besides, there will be a lot of like auditing and everything. So while some of them might have an edge right now, I think that long term, this is just uh, something like pretty ordinary that will be like, okay, something that's running under the hood. That is to say, if we are successful as zk, people won't know they are using zk, much as ordinary people don't know about TLS or other things. So um, yeah, I don't know if I answered like all the questions, but uh, we can like continue chatting.
Out of interest, how's the support for different VMs implemented?
The problem is right now every VM has its own like custom verifier because they have like a slightly different architecture. Maybe they organize some things differently, and so each has their own code. But in Aligned, incorporating a new verification code is really easy. So you would have, I don't know, the RISC-0 code, the SP1 code. You just add them and people would know, okay, this is a RISC-0 proof, this is a Nexus proof, and so you would just call the relevant thing. Of course, then you could, I don't know, get to a common format or something so that all the proofs, you don't have to have a custom verifier for each of them. The good thing is you just have to write it in Rust. It's not that you have to code in Solidity, which is like a bit painful because you have to pay attention to lots of things. Here it's more like you coded your verifier and we can add it. It's pretty straightforward. Maybe for some things written in C++, we have to make new bindings, but it's pretty straightforward.